Okay, so what I want to move on now is, we're playing the semantics versus syntax game. The next step that we took in the propositional calculus was the compactness theorem. We have the same compactness theorem in first order logic, but it is going to be, we will need a different proof. So we have here syntax, semantics. I will not repeat everything, but here we have the compactness theorem. But we will not prove it directly. In order to prove it, we will go through a proof system, formal proofs, and then we will show the soundness and completeness. So soundness and completeness are going to be exactly the same as we saw in propositional logic. So without introducing, we have not yet introduced the formal proofs. But what I want to say is that we will need the soundness and completeness in order to show the compactness theorem. So I will not prove compactness now, but I will still state it, and show you what we get out of it. But we will postpone the proof of the compactness theorem until we have the formal proofs and the soundness and completeness. We cannot have a direct proof like we had, a non-syntactic proof like we had in propositional logic. Okay, so this is where we are now. So what is the compactness theorem? Exactly like we had in propositional logic. Theorem for first order logic. It says that a set of well-found formulas is satisfiable if and only if every finite subset of it is satisfiable. So it's exactly the same theorem. What changes is our meaning of what are well-formed formulas. Here they are first-order logic formulas. And the meaning of what satisfiable means. Satisfiable in a proposition logic meant that you have a truth assignment. And here it means that you have a structure and maybe an assignment to the structure that makes all the formulas in sigma true. Now, as in the propositional logic, we can use it to show both positive and negative results. So let me start with a negative result, then we will get into a very interesting positive result. So we are not proving it now, we're postponing the proof, but we will see some applications of compactness. So applications of compactness. And our first application will be non-definability result. So just recall that a family of structures is definable in some language L if there exists a set of L WAFs such that So let the family of structures give it a name, say K. And the set of roughs, let's give it a name, sigma, such that the set of M such that M satisfies sigma equals exactly K. So the notion of definability is the same as definability that we had in propositional logic. It's just that it applies to a family of structures rather than to a family of truth assignments. And if I don't want to worry about assignments S, so let us assume that the elements of sigma have no free variables. If they don't have any free variables, we don't need any assignment S. So it just makes it a little bit less cumbersome. So we assume that those have no free variables, therefore we don't have to worry about assignments. So we had some examples last time. So for example, we had maybe the first example, non-trivial example that we saw was that the set of all infinite structures is definable in every language L. Every first-order language L, we can define it. You remember we had those formulas. We had sigma infinity was the set of all phi n such that n is a natural number, where phi n basically said there exist at least n elements. So that's not difficult to say. There exist x1, x2, up to xn, so that all of them are different. So if we take a set of formulas that for every n says there exist at least n elements, a structure will satisfy it if and only if the structure is infinite. So that's a set of sentences that defines the family of all infinite structures. We talked about it last time. But now I want to show you an example of something which is not definable. So now let us consider a family of structures that look very, very similar. So what about K finite, which is the set or family of all finite structures? How shall we define that? So we can define a set of all infinite structures because we say you have at least 3 elements, at least 4 elements, at least 5 elements. If you satisfy all those requirements, you must be infinite. But what about being finite? Now, the problem is that if I want you to say you are finite, I would say either you have at most 2 elements, or you have at most 3 elements, or you have at most 4 elements, and so on. But when I write a set of formulas sigma, it means I want to satisfy and phi 1 and phi 2 and phi 3. I don't have a way of saying or over an infinite set. Even as a set of formulas. I mean, if I write a set of formulas, it's like I've required and over all of them. But I don't have a way of saying or over all of them, even if I use an infinite set of formulas. So we want to, it turns out that it's really impossible. We cannot define the set of all finite structures. So the claim is going to be claim is that K finite is not definable. There's no way we can come up with a set of formulas that will define K finite. Now, non-definability looks like a difficult thing to prove, because for definability, you have to come up with an example sigma. For non-definability, you have to show me nothing will work. And for that, we will use compactness. So the proof uses the compactness theorem. So we will argue by contradiction. So assume by way of contradiction that some sigma finite defines K finite. Assume that we do have such a set. And now we will consider a new set of formulas. So we construct now, striving towards a contradiction, we construct a set of formulas. So let gamma be the set that we just saw here. Sigma infinity. So the set of all phi n, n in n, where phi n is just the formula, there exists x1, there exists x2, there exists xn, such that all of them are different. How will I write it formally in a kind of concise way? We will say such that end over all I not equal j, ij less or equal n, that not xi equals xj. So phi n says there exist n members such that no two of them are equal. So phi n says there exist at least n elements. Okay, so let's see what we had here. We assume, we want to show that the set of all finite structures is not definable. We assume by way of contradiction that we do have a definition. Now we consider a different set. Now I'm asking, is sigma finite union gamma satisfiable? What do you see? What do you think? Sigma finite defines the set of all finite structures, and gamma actually says the structure to satisfy gamma must be infinite, because gamma says there are at least n elements for every n. So is the union satisfiable? No, because this requires no, since every structure satisfying sigma finite is finite by our assumption that sigma finite defines the set of all finite structures, and every structure satisfying gamma must be infinite. So I cannot have a structure that is both finite and infinite at the same time. Okay, so far so good. I constructed a set of unsatisfiable formulas. But now comes the catch. If we invoke the compactness, we can argue that this set is satisfiable. So now I make this subclaim. So how should we call it? I call the whole thing claim, so this should be subclaim. Every finite A subset of sigma finite union gamma is satisfiable. That will lead to a contradiction. Because by compactness, if every finite subset is satisfiable, the whole set should be satisfiable. But we know that the whole set is not satisfiable. So how do I show that every finite subset is satisfiable? Just consider a finite set, a finite subset. So what should be a finite subset? So I have here sigma finite, which I don't know what it contains. So I have here sigma finite that contains all kinds of formulas, phi 1, phi 2, all kinds of things. This is sigma finite. I have no clue what it contains. And then I take a union with this set gamma 1, phi 1, phi 2, phi n, and so on. This is gamma. Now I take an A, which is a finite subset of the union. So A takes some of these guys and some of these guys. But the main point is that since A is finite, there is a maximum n such that phi n is an A. So let n be the maximum index of a member of gamma phi n in A. There is such a maximum index because A is finite. If it's finite, it cannot take everybody. Let M star be any finite structure whose universe has more than n elements. I claim that this M star will satisfy A. Why will it satisfy A? Because in order to satisfy A, so now I claim that M star must satisfy every formula in A. Because every formula in A, either it came from sigma finite, because given any, let us give them a name, say phi in A, is either a member of sigma finite. If it's a member of sigma finite, why does M star satisfy it? What? Because M star is finite. And sigma finite is satisfied by every finite structure. So M star satisfies phi since M star is finite, and sigma finite defined all finite structures. So every finite structure satisfies everything in sigma finite. Or if it's not a member, or otherwise, phi equals some phi I for I less or equal n. Right? If it didn't come, if I pick some phi here from A, I pick some phi. Either it came from sigma finite, so it's satisfied because I have a finite structure. If not, it came from here. But if it came from here, since n was the maximum index of a phi that came from here, this phi has index at most n. So what does phi says? Phi says there are at least I many elements. But I picked a structure that has more elements. This is since M star has more than n elements, M star satisfies this phi I. So we showed that the M star that I picked satisfies every formula in A. So you see, we constructed this set, which is on one hand clearly not satisfiable, because this requires every satisfying structure to be infinite, and this requires it to be finite. But on the other hand, every finite subset of it, we showed, is satisfiable. So we got a contradiction to the compactness, contradicting the compactness theorem. So using the compactness, we managed to show that the set of all finite structures is not definable. So this is the kind of logic that I want you to be able to use. So let's do more examples. But the reason I'm showing you this is that this compactness has very interesting consequences that we will hopefully see today. Okay, so you see what was our reasoning. We assumed by way of contradiction that some sigma finite defined our structure. We added this infinite definition of infinite structures and showed that every finite subset is satisfiable. Let me give you another example of the same type of argument so that we'll somehow get more used to this argumentation. So now instead of just talking about the size of a structure, and here the language didn't matter, let us look at the language for graph theory. So we have a language with one binary relation, and a structure for this language is a graph, where Rxy means there is an edge from x to y. Okay? So second example. Consider the family of graphs. So for us, a graph is a pair, vertices, and edges. And we say that a graph has diameter n if you can get from every point in the graph to every other point in the graph by taking at most n steps along edges. So I can talk about the diameter of the graph. Have you seen this notion before? So if I have here Say I have here 10 points or whatever, and they're all connected. So say my graph is the points A1, A2, A3, A4, A5, A6. What is the diameter of this graph? It's a question of what is the maximum number of steps that I need to take to get from one vertex to another. So here the diameter of the graph is 1, 2, 3, 4, 5. And now if I add, say I add one node here, A7, and say I connect it to everybody. So what is the diameter of this new graph? 2, because now I can get from any point for any point in 2 steps. So that's the notion of a diameter of a graph. How many steps along edges you need to take to reach from any point to any point. Okay? So let's write it formally. So say that the diameter of G is A K if there is a K long, okay, if for every U, V in the set of vertices, there is a path U, V1, VK, V, such that UV1 is in E for all I, VI plus 1 is in V, and VK, V is in E. Is in E. So that's a natural thing. I have a path of K many edges that connects U and V. So in that case, I will say that I have the diameter of a graph is at most K. To say it's exactly K, I will have to, I have here K minus 1, you think?
Yeah, it should be K minus 1.
K minus 1, okay. Yeah, I can never figure out the plus minus 1. Thank you. Okay, so I have a notion of a graph having diameter K. It has diameter exactly K if I have 2 vertices that cannot be reached with a shorter path. Okay, so now let us start by defining something that we can define. Can you find some sigma diameter that defines the set of all graphs of infinite diameter. That is, the diameter is not finite. So how shall I say the graph has infinite diameter?
That graph is not connected.
Yeah, but you want to say it in the language. This is in the language. Oh, I didn't tell you the language. In the language L that consists just of a two-place relation. That's what you have to work with. This is the edge relation. So we have a two-place relation standing for edges. This is our language. So I cannot say the graph is not connected because I don't have the word connected in my language. In my language, I only have this and first-order logic. So how will I still say that a graph has infinite diameter? By the way, it can have infinite diameter without being disconnected. Because you can have a graph which is infinite diameter, it could look like this. It could be disconnected, of course, but it could also look like this. That I have this guy, and then this guy, and then this guy, and then this guy, and so on. So this kind of hydra has a leg for every length. So now the diameter is infinite because I cannot say that every 2 points can be reached by k steps. For every k, I can find points which require more than k steps. So how shall we write a definition of the set of all graphs of infinite diameter? But it's true that if a graph is disconnected, it is infinite diameter, but not necessarily. It's not if and only if. So how shall I write that? What will be this sigma diameter? What shall we put there? How shall I say the diameter is not 1? 1 is not an upper bound of the diameter. Yes?
If you're just going for not 1, you can just say there exists an x and there exists an y such that there is no edge between them.
Exactly. Right. So I will have these formulas, sigma diameter. We'll start with saying there exists an x and there exists a y such that not our xy and not our yx. There's no edge between them. So this tells me the diameter is at least 2. In one step, I cannot make sure that I will connect. Right? And now I can say, of course, so how shall I continue now? What will be my nth formula? How will I say that the diameter is not n? Any of my yes?
There exists x, there exists y, such that it doesn't exist v1, v2, up to vk.
Right. There exists x, there exists y, such that there doesn't exist. So, such that I can use for all, I can say it does not exist, such that it's not the case that there exists v1 up to vk plus 1, such that x v1 r of x v1 and r of v1 v2 and r of vk minus 1 y. Did I put enough parentheses? So there exists x, y, such that there do not exist a chain of k steps connecting them. Okay? And then we will continue and put such a formula for every n. So let's call this formula psi n. So psi n tells me the diameter of my graph is at least n, because there are 2 points that cannot be connected by less than n steps. So if you put all of those psi n's together, we know that our graph does not have a finite diameter. Yes?
Doesn't this definition fail in some cases? For example, if you had like a cycle of length 4, then there exist 2 vertices that can only be connected by a path of length 1 or a path of length 5 or a path of length, like with the remainder equal to 1. But there exists no path have certain vertices that can only be connected by
certain lengths of paths.
certain lengths that don't
Right,
include k.
but if I make this requirement that for any n, there exist two elements that cannot be connected by n steps, and I put them together, then I exactly defines the graph of infinite diameter, right? Because if a graph is infinite diameter, for every n you have 2 points that cannot be connected by. I'm not saying that the positive side. I'm saying the negative side. You have 2 points that cannot be connected by n. Cannot be connected by n plus 1. You have 2 points. For every n, you have 2 points that cannot be connected by a path of length n. Okay? Okay, so we have this set of all phi n's will give me a definition for the set of all graphs of infinite diameter. Now I'm claiming that similarly I can, yes?
Shouldn't we use consistent subscripts there? So like shouldn't our b's be like n plus 1 and all that instead of k because there's no relation to what k.
Oh, you're right. What I called it phi n. So I should call it phi k, sorry. That's consistent now? Sorry.
Sorry, it was bugging me.
No, you're completely right. We are doing formal logic. We have to be formal.
Why is the last k plus 1? Why is it k plus 1?
Oh, it's k minus 1. Right. It's k minus 1. Okay, so my claim that my mistakes are only by 1, additive 1, now I got a counterexample. I had a mistake by additive 2. Right. I used to have professors that whenever they made such an error, they say, I made it intentionally to see if anybody is listening. But I think I never in my life passed an exam with a perfect score. I always make such mistakes. It's too late to change. But it's good that you notice, and it's good that you correct it. And anybody that thinks it deserves a bonus point, just email me and you'll get it. Okay, so we have this definition. Now comes my claim that says the family of all infinite diameter graphs is not definable. So it's a very similar situation to what we saw with finite structures.
Should I be finite diameter?
What? Sorry, that's a good one. Yeah. We just defined the infinite. Yeah, that was brave, but it paid. Yeah, you're right. Okay, so this is not definable. Now, how shall we do it? We'll do it the same kind of argument. So the proof will be very similar. I just want you to get used to this type of argument. So the proof is assume by way of contradiction that I have some sigma star defines the family of all finite diameter graphs. And now we're going to use this union again. So now we are going to consider sigma star union sigma diameter that we had here. the union of these two sets. Two sets of sentences. Now I can ask, is it satisfiable? Is sigma star union sigma diameter satisfiable? And what is the answer? This is defined as the family of all finite diameter graphs. This defines the family of all infinite diameter graphs. I cannot have a graph that both has a finite diameter and an infinite diameter. So the answer is no. Now we are going to show that every finite subset is satisfiable. However, pick any subset, any finite A, subset of sigma star union sigma diameter. And I want to show that such an A is satisfiable. So again, it's the same kind of game. I'm saying I have here sigma diameter that has those phi k's. Phi k's say the diameter is at least k, or is greater than k, right? So let n be the maximum index of a psi k in A intersection sigma diameter. Remember, sigma diameter is the set of those psi k's, and A is a subset of the union. So I look at the maximum index that got into A. There is such a maximum index since A is finite. Now we want to construct a graph. Let's call it Gn that satisfies A. How shall I construct such a graph? I want to construct a graph that satisfies all the formulas in A, and I know that the maximum index of a member of a type psi that got into A had length n. So I know that I should require that there are two vertices that cannot be connected by an n path. On the other hand, since I'm satisfying the definition of finite diameter path, my graph needs to have a finite diameter. So can you describe a finite diameter graph that does not, that its diameter is more than n?
Yeah, it does define itself.
Well, so what will it be?
You get any graph that has a diameter.
Yeah, but give me a, we can have a concrete one, right? So we just have Gn. We can exactly tell you what it looks like. So let Gn be, I can either draw it or I can define it formally, but it is just going to be a set of, say, just to make sure that I'm not getting into my +1, -1 problem. So I have here a V1 up to Vn plus 100. And my edges will just go from each Vi to Vi plus 1. Right? So the set V will be V1 up to Vn plus 100. And the set E, the set of edges, will be the set of all Vi plus 1, such that I is less or equal 99. So since Gn has finite diameter, it satisfies sigma star, and therefore A intersection sigma star. That is, it satisfies all the formulas in A that came from sigma star. And since the diameter, let's write it like this, diameter of Gn is more than n, it satisfies every phi that is in A intersection sigma diameter.
Your index, shouldn't it be n plus 99?
What?
Connected from 1 all the way to n plus 99 rather than just 99.
What? How can I?
The index on the edge. True.
The index.
I has to go to n plus 99 because you have to connect the first n before you connect the other.
Oh. I thought that I'm safe against. Oh, wow. Yes.
I just have a question then. Is that the concrete example of G of n is necessary in the proof? Or we can just say that there is...
You have to prove that it exists. So we have to somehow argue why there exists a graph of arbitrary diameter that is still has finite diameter. So the best way to argue it is by showing an example. Right? So A is just the union of these two sets. So A equals just A intersection sigma star union A intersection sigma diameter. So if I satisfy every formula here and every formula here, I satisfy every formula in A. This is just a way of saying the formulas in A came from either the left-hand side or the right-hand side. So if I made sure that I satisfy every formula in A that came from either side, I satisfy all of A. So we get a contradiction to compactness. Right? So Gn satisfies A. So we had the same argument for both proofs, for the proof that the set of finite structures are not definable, and for the proof that the set of graphs of finite diameter is not definable. And both of them use the compactness. And now I want to use the compactness in a positive way. So far I use compactness in a negative way. I use compactness to show you certain tasks are not doable. But now I want to show it in a positive way. So the way I'm going to show it in a positive way is, it's a very interesting idea. It's called the non-standard model of arithmetic. So among all the structures that we discuss, there is one language and one structure that are most important in math. And this is the structure of natural numbers. Most of the mass that we really use can be just generated, built from the natural numbers. So the natural numbers is the most interesting structure. So we consider here, so let us consider a particular logic. Let us consider a language for number theory. Okay, so what is my language? So we can be generous, put there whatever you want. So I want to have there, say, some function f that will stand for addition, and some function g that will stand for multiplication. And I want to put there, so this is addition, this will stand for multiplication. For now, it's just a language. I want to put there, if you want, r, two places that it will stand for less or equal, then I can put a and b constants for 0 and 1, and we can add more stuff. So this is going to be some language. Let's, for concreteness, assume that this is our language. So this is my language. And let the model of the natural numbers consist of the universe is the natural numbers, f is plus, g is times, r is less or equal than, a is 0, and b is 1. So now I'm looking at a specific structure for this language. And now I want to describe this structure. I mean, since our formal language of talking about mathematics is first-order logic, I want to try in first-order logic to describe the natural numbers. So I want to put all kinds of requirements. I can put the requirements, the addition is commutative. I can put the requirement, the multiplication is commutative. I can put the requirement, there exist infinitely many prime numbers. I want to make my best effort to describe the natural numbers. So what will be my best effort? My best effort will be, I will take this infinite set, which is called the theory of the structure, which is defined, the theory of n, which is defined as the set of all phi in the language, such that phi is a sentence of L, so that this structure n satisfies phi. So the theory of a structure is the set of all sentences that are satisfied in this structure. So it's the maximum that I could have said about the structure. Everything that's true about the structure, I threw it in, implicitly. So this is the theory of a structure in a certain language. Now, the question is, okay, so I did my best effort to describe the structure. Did I do a good job? Does it really describe the structure? So this reminds me, I mean, I don't know how things are being done today, but in my old days, if you wanted to go on a dating service, you could write a set of requirements from your desired partner. So you say, you know, he should be tall and handsome and athletic and have a lot of money and whatever you write, all the requirements. And then you know what happens. They match you someone and you see them and you feel like, oh, what am I doing here? How do I run away? And they can say, oh, but it satisfies all the requirements that you gave us. And you realize that there were some minor issues that you forgot to write, like they should not have a terrible breath smell, or they should, whatever, wash their hair once in a year or at least. So it turns out that this problem is not just a problem in real life, it's a problem in math. So I wrote here all the requirements. I was trying to describe the natural numbers. That's a basic structure in mathematics. And I claim that in spite of doing this wonderful effort and writing an infinite set of requirements, I still fail to describe it. I can get in the package something that satisfies all my requirements, but it's not what I wanted. So here is my claim. There exists a structure M that satisfies every sentence in the theory of N, each of my requirements, but is very different from N. What do I mean by very different from N? I will make it precise. In particular, it has an element with infinitely many predecessors. With infinitely many numbers that are smaller than that. So I was trying to describe the natural numbers. I wrote all the possible requirements. There's going to be a structure that satisfies all of those requirements, but is not the natural numbers, because in natural numbers, every number has only finitely many predecessors. And in this new structure M, there are going to be infinitely many predecessors to some of the guy. So such an M is called such an M, and M is called a non-standard model of arithmetic. Now, we are going to use the compactness theorem to show that such a non-standard model exists. But to motivate you, let's try to think a little bit about how such a non-standard model look like. So, how does such an M look like? So what do we know about it? So you see, we can know a lot about it because we know it satisfies every statement that is true in the natural numbers. So I can ask you, does this M has a first element? Does it M has a first element or not? Yes. Yes. Because in a natural number, there is a first element. Does it have a last element? No, because in natural numbers, there's no last element. Everything we can say in this language should hold for this, let's hold for the natural number, should hold for. So we know that it looks like this. There is the first element, say 0, then there is a 1, then there is a so on. But so we have here kind of, we must have a first element, we must have a second element, we must have a third element. For any n, we must have an nth element. Still, there is an element here with infinitely many predecessors. So there is some crazy guy here, let's call it, I don't know what, D, some strange element here that is above all of those. Okay? But that's not enough. Is there only one such element? Why are there infinitely many?
Because there's no maximum element. You could always do like the successor to D.
Right. Then there is a successor to D. There is D plus 1, because every number has D plus 1. And there is D plus 2. So it goes like this. Right? But it's not only that, because there's also D minus 1. Because for every number that is not 0, D is not 0. For every number that is not 0, I have the predecessor, the immediate predecessor. So there's also D minus 1. So now I see that this D lives in a whole array. What does it look like, this guy? It goes infinitely to the future and infinitely to the past. Or So which kind of familiar set of numbers does it resemble? The integer numbers, right? It's like Z, the integer numbers. It's like a copy of the integer numbers, right? Because everyone has a predecessor, immediate predecessor, and everyone has an immediate successor. So it looks like a copy of the integers. But is it everything? I claim that this is not enough. It's worse than this. Because now look at D plus D. So if we consider where should I put D plus D? Because I have plus, right? So I need to have D plus D. Where can I put D plus D? So since D is greater than every n, I can say that for every n, D plus D is greater than D plus n. Right? Because D is greater than n. Because I can say that for every x, for every y, for every x, for every y, if x is greater than y, then x plus x is greater than x plus y. This is a formula that holds in the natural numbers. I mean, plus I should write as f, and greater than I should write as r, but this formula holds in natural numbers, so it should hold here. So d plus d is greater than d plus n for every n. So it cannot live in this copy. There is some guy, it's somewhere here. It is above every d plus n. So d plus d lives here. But this guy also has an immediate predecessor, an immediate successor, and so on and so forth. So here lives a whole other copy of z. Right? And now I can ask you, I mean, are there any only two copies of z floating there in the air, or there are more? There are infinitely more, because there's also the copy of n times d for every d. Okay, but that's not enough. Because d plus d, d times d is going to be above every n times d. So this guy is even further away, right? It's not the end yet, because what I claim is even that between any two copies of these lives another copy. So those copies are dense. Can you show me why can I show that between any two copies there is another copy? I'll just take the average. So you see, if I have here some d, and I have here some d prime, I know that either there exists an x such that x plus x equals d plus d prime, or there exists an x such that x plus 1 equals d plus d prime, right? I mean, every number is either even or odd. This is a statement that holds in the natural numbers. Every number, either I have its half, or I have, so that x plus x, I don't know, equals d plus 1. Either the number is even, so I have an x such that x plus x equals this number, or the number is odd, so I have an x such that x on x equals this number plus 1, or minus 1, it doesn't matter. But this x is not going to be a member of any of these two. This x is going to live here in a new copy of himself between the two. Because it's easy to see that this x should be greater than, it should be greater than d plus n, and it should be less than d plus d. So anyway, so we can show that it's dense. So what we get is that, now just see what happened. I mean, we were trying to describe the natural numbers. We were trying to come up with an ad on our Cupid that our only candidate will be the natural numbers. we try to describe the natural numbers. It's very important for math to be able to say what are we talking about in math. If we cannot tell us what are the natural numbers, how can we communicate with each other? Maybe each of us has a different image of what the natural numbers are like. Maybe for you this is a natural notion of natural numbers, and it's only me that was thinking the natural numbers is only this part. If we want to communicate, we have to be able to describe them exactly. So here, I did my best effort to describe it. I wrote all the formulas that are true in the natural numbers. And yet, I got something which is very, very different. It not just has one element which is bigger. It has this whole thing. You can show that this thing looks like the rational numbers, where I replace every rational number by a copy of z. So it's huge. And still, it satisfies every requirement from the natural numbers. So this is called the non-standard model of arithmetic. And those non-standard models, they kind of creep in. We cannot prevent them. We cannot keep them out. And there was even an attempt to say, what happens if the natural numbers are a basis for doing math. So based on the natural numbers, we define rational numbers. And based on the rational numbers, we define real numbers. What will happen to rational numbers and real numbers if the naturals that I start from look like this? So that's something interesting to think about, because what will happen now is that, now look at what happens to the rational numbers which are based on this non-standard model. So now I'm looking at the rational numbers. And so just look at this. Say here is 1. Now I'm instead of having a telescopic view, I'm having a microscopic view. So say here is 1, here is a half, here is a third, here is some 1 over n. What will happen to 1 over d? Where will 1 over d be? So it will be 1 over d will be closer to 0 more than any 1 over n. All of those guys, the 1 over all of those guys will squeeze, will fold in backwards into this space between all the 1 over n's and 0. So they're going to be infinitesimal numbers. Numbers that are smaller than any 1 over n, but they're still not 0. Because for every number, 1 over this number is bigger than 0. And such infinitesimal numbers, 1 over non-standard numbers, there are several attempts to use them to model situations. So the first one attempt was to say, when we talk about calculus, we talk about limits, we talk about derivatives, we talk about continuity. Over and over again, you have to say for every epsilon there exists a delta such that. And here you can rewrite all of calculus, but instead of talking about for every epsilon there exists a delta, you talk about those infinitesimals. So the derivative of f, if usually the derivative of f at a point x0 is the limit, I don't know if you remember it, but if you do, you should correct me because I'm going to make mistakes. It's the limit as h goes to 0 of f of x0 plus h minus f of x0 divided by h. Right? That's our definition of the derivative. Right? And I need to use limits. But I could instead define the derivative of f of x0, if I have those guys, as just being f of x0 plus d minus f of x0 divided by d for some infinitesimal d. For some d that is, not for some d, but this is 1 over d, and this is 1 over d. The 1 over d is a small number, such a small number that it's smaller than every n. So if I calculate f at this point and divide by this small number, I'll get the limit. So it's a way to present calculus without limits. It's also a way that people try to reason about economy. Because what happens if you believe that the prices in the market are being determined by demand and supply, right? That's a very common. So now if I go to the supermarket this afternoon and buy an orange, the price of oranges should go up. But by how much does the price of oranges go up when I went to the Zers and bought one orange? I mean, so there is an attempt to model economy using those non-standard numbers. Okay, so we have this, in summary, we have this notion of non-standard models of arithmetic. We cannot prevent them from creeping in. Even if we write all the possible requirements, there will still be such non-standard models, and they have all kind of interesting properties. And now I want to show you that this basic claim really exists. I mean, it really holds. So here is my theorem. So let us just write the definition and the theorem, and probably we'll have to postpone the proof to next time. So here is my definition. A structure M is a non-standard model of arithmetic if it satisfies every sentence in the theory of n. So the theory of n are all the sentences that hold in the natural numbers. And it has an element with infinitely many predecessors. Let's make it non-standard. It is a model of arithmetic when it satisfies the theory of arithmetic, and it's non-standard where you have this crazy element. And now we have this theorem that says non-standard models of arithmetic exist. So the main important notation here, which is I introduced only today, is this notion of the theory of a structure. So we fix the language, we fix the structure, and we look at all the sentences that hold in this structure. That's the theory of a structure. Okay? So now, how are we going to prove it? We're going to use compactness. So what we are going to do is we are going to, so maybe I have 2 minutes to just describe the idea, proof idea. Let us expand the language. Let us expand our basic language L used to define the theory of n by adding a new constant symbol C. So the language now has one more constant symbol. So I have this language L prime that has this F, G, R and A, B, C. I added a constant symbol to the language. Still, everything that's written here is in the language L prime. It just didn't use C. And now we consider the following set, the set theory of N union the set of all phi n, n is a natural number, where phi n just says that C has more than n predecessors. So it says there exist x1, there exist x2, there exist xn. We know how to say all different. We've said it several times. Such that C is greater from x1, C is greater than x2, C is greater than xn. So I'm saying C is greater than at least n many numbers. But I say it for every n. So now note that if this is satisfiable, a structure that will satisfy it will be a non-standard model. Because the interpretation of C in this structure will have infinitely many predecessors. So now we just need to show that this is satisfiable, and we will do it by compactness. But we'll do it on Thursday.